Okay, three concepts in this one. We're going to relate the idea of simple harmonic motion, a back and forth motion or up and down motion, to uniform circular motion that we've already discussed. So starting off with a video. So you can see in this video that the green ball going around a circle, if you measure its vertical position and have the red mass at the end of the spring match the vertical position of the green ball. So the spring is only moving up and down, and then you turn that circle on its side, then you see that an edge-on view of uniform circular motion gives a back and forth oscillatory motion. In fact, it gives something called uniform circular motion. Okay, we'll answer that next question in a little bit. Where does the displacement, speed, and acceleration reach their maximum values? Okay, so this is the idea here. If you have an object that is moving in uniform circular motion, so this is an object on a turntable that's executing circles, that blue ball, and then we have a light source that shines light on this, then there will be an image of that blue ball on the screen. And if we use like an old-fashioned strip chart where you're rotating this spool of paper, then you can inscribe what's known as uniform circular motion. If you take this strip and turn it on its side, you can see that the horizontal, in this case it's horizontal, the video had a vertical displacement of that spring. In this case we're thinking about it being horizontal. Then that horizontal displacement of the ball here from the equilibrium position looks like this as a function of time. And you say, well, that looks like a lot like a cosine curve, and I would say, yeah, that's exactly right. So here's how it works, and here's where we're starting to get a little bit of mathematics into this problem. I've got the light source, I've got an object that's going around in circular motion, uniform circular motion, but I'm only interested in its horizontal component, its x component. So when it's here, its x component is equal to the radius of the circle, which we're going to call A, the amplitude. It's called the amplitude. That's its maximum position. So if we're just looking out to here, this maximum position that it can go to is called A. In the uniform circular motion, when it gets to here, then the x component, so x is measured to the right. At this position here, y is not 0, but x is 0. And so it's going to be sitting right here at x equals 0. When the object gets over to here, x is going to be equal to minus a, because x is measured positive to the right, negative to the left. And so here we'll have x equals minus a, back to x equals 0, and then back to x equals a again. So what we see is that x, as a function of time, this horizontal component of the uniform circular motion has this oscillatory behavior like we talked about before. And just as we've done with uniform circular motion, we define the period to be the time required for one complete oscillation. So start here and go here, and that will be the period. Or you start as it's crossing the axis right here, and again where it crosses an axis in the positive direction, here it's crossing the axis in the negative direction. So to go from here to here, that also gives the period of one cycle. Remembering that this is the time axis, and the period is the time for one complete oscillation. So the angle, and the way that you relate the angle of this ball going in uniform circular motion to the time is to say that the angle in a time equal to the period, if t equals the period, and we plug that in here, then we'll have theta is 2 pi times the period divided by the period. Well, that's pretty neat because the periods cancel and we get 2 pi. So that says that one complete cycle, meaning I've gone from t equals 0 up to t equals the period, gives us a rotation of 2 pi radians, which is one complete circle. So that's how the angle relates to the time. And then we define something called omega, the angular frequency. Now this is very similar, and it has the same units as angular velocity that we talked about in the rotation chapters. This is given by the Greek letter omega, and it's measured in radians per second. And we'll say a little bit more on the next slide. But this omega is defined as 2 pi divided by the period. And if you're confused about how that relationship works, just remember that omega is like an angular speed, but in this case, it's an angular frequency. It's measured in radians, and for a complete circle, it's 2 pi radians. Divided by a time, and for a complete circle, the time is the period. The curve that we're seeing here looks like a sinusoid, but actually it's a cosine. If we start this ball right here at time t equals 0, then x will be a at time t equals 0. So at time t equals 0, that's that spot here, and x equals plus a. Then at this point here, that's where x equals 0. That's this point over here. This point here, we're at x equals minus a, that's that one. At this point here, we're back up to x equals 0. And then here, we're back to where we started again. So x is a cosine omega t. So that's where that comes from. I just wanted to show you so you can see, instead of just giving you the equation, to show you kind of where it comes from. All right, define the period frequency, angular frequency, amplitude, and displacement for simple harmonic motion. Period, t is the period. It's the time for one complete cycle, seconds per cycle, or just seconds. It's the time for one cycle. The frequency is 1 over the period, just like we did in uniform circular motion. And that's in cycles per second. So I've taken these units of seconds per cycle and inverted them to get cycles per second, same as we did in uniform circular motion. Omega is 2 pi f. The other way that we just wrote it in the last slide is 2 pi over t. And you can remember it either way you want to. This way reminds you that 2 pi is in radians, period in seconds, and omega is measured in radians per second. This way, omega is 2 pi f is also a convenient way to write it. And now you can see that the angular frequency measured in radians per second, and you can see that from here too. 2 pi is measured in radians. F is cycles per second. So that'll give you radians per second, and there's a cycle in there that's not really a unit either. But that, then the amplitude. So this amplitude, this is an important one. The amplitude is measured in meters, and it is the maximum displacement from equilibrium. It's not, if it's oscillating like this, it's not the peak-to-peak distance. It's a distance from the center point, the equilibrium position, either vertically upward or downward. It's half of the, it's the maximum displacement from equilibrium. So if it's oscillating back and forth like this, and this is the equilibrium position, then the amplitude is this distance here to the right, or you could also measure it to the left. In fact, the total distance that it covers back and forth is twice the amplitude. And then the time-dependent displacement is what we wrote down in the last slide, a cosine omega t. The reason we have an a there is that the cosine function normally goes between 1 and minus 1. Right? That says 1 if you can't read it. But this guy is oscillating between a maximum displacement of a and minus a. Here's another place that you can understand what the amplitude is. Here's x equals 0, here's x equals a, and that distance is a. And from x equals 0 down to x equals minus a, that distance is also a. So the total between the maximum position and the minimum position is actually 2a. Okay. An object is in simple harmonic motion, and the rate at which the object oscillates may be described using the period t, the frequency f, and the angular frequency omega. If the angular frequency decreases, what's the effect on the period and the frequency? So we're going to have an angular frequency that decreases. So omega is going to go down. What happens to the period and what happens to the frequency? Without looking at these answers, let's try and figure it out. Well, omega equals 2 pi f. And omega is 2 pi over t. Those are the two relationships we've talked about. In fact, these are both, it's easy to go between these two because you know that the frequency is 1 over the period. So if you can just put in 1 over t for frequency here to get this equation. Lots of ways to remember it. All right, well, if omega goes down, then since omega and the frequency are proportional to each other, then the frequency must also go down. Since omega goes down and omega is inversely proportional to the period, then the period must go up, must increase. Period must increase. Let's see which one of these answers. The frequency decreases, the period would remain the same. That's certainly not true because the period has to go up. Period would increase, but the frequency remained the same. The period and the frequency would decrease. No, one of them goes up, one of them goes down. The period and the frequency would increase. The period would increase, that's right, and the frequency would decrease. So this is the one that we want. Just a reminder from Chapter 8. We'll need these concepts in order to fully appreciate uniform circular motion. I'm sorry, simple harmonic motion. So remember this concept where we talked about the tangential speed of an object undergoing uniform circular motion. We found that the tangential speed is r times omega. The other piece of this that we're going to need is this acceleration, r omega squared. So the radius out here is a. The speed is a omega. If r equals a, then that tangential speed will be a times omega. No big deal. That's how fast it's going around the outside. And then finally, the acceleration. What direction does that acceleration point? And you say, in toward the center, because it's uniform circular motion. And I say, you're absolutely right. So the acceleration is going to be inward toward the center. It's given by r omega squared. And if r equals a, then that acceleration is a omega squared. Okay? That's for uniform circular motion. Let's see what this looks like for simple harmonic motion. A, the acceleration vector is shown here with a green arrow. So at any given point in time, as this blue object executes this uniform circular motion, its acceleration vector is always going to be pointing toward the center of the circle. And the magnitude of that acceleration is a omega squared, where omega is the angular frequency, aka the angular velocity of the object going around a circle. But that always points toward the center of the circle. What we're interested in, let me also point out the speed. Here's the velocity vector shown in red arrows. Velocity vector, as you remember, always points in the direction of motion. Wherever that thing is headed, that's the direction of the velocity vector. And that velocity vector has a magnitude, well, is the speed of it actually is a times omega. And then finally, r equals a. So what we'd like to do now is to ask the question, for this x component, if we're going to convert this uniform circular motion into simple harmonic motion, then we're only looking at motion along the x-axis. So it's just oscillating along x, going back and forth like that, just like in the video that we showed. So what's the maximum position, maximum x value? And you say, well, I know that. If it's right here at this point in the circle, I'm as far in the positive x direction as I can be. And how far is that? Well, it's a. So x max is going to be a. X min would be over here, and x would be minus a. Well, we're just concerned about the maximum right now. What about the velocity? The x component of the velocity. Take a look at this red velocity vector. Here's the x-axis. Here's the y-axis up here. What is the x component of that velocity vector? And you say 0. And I say, right. Velocity is pointing that way. This is x. The x component of that velocity is 0. So that's kind of embarrassing. That says that the maximum x value does not occur where the maximum velocity occurs. Where does the maximum velocity occur? Let's take a look at this point here, Vx. What is the x component of that velocity? And you say, well, let's see here. X is to the right, that velocity is to the right, and the magnitude of that velocity is a times omega. Therefore, the maximum possible velocity you can get for simple harmonic motion is a times omega, and it occurs here and here. So we get maximum velocity, or max min velocity. In this case, the velocity is negative. These 2 points, we get the max and the min displacement. What about the acceleration? That green arrow is the acceleration vector. X is pointing to the right. What is the component of that green acceleration in the plus x direction? And you say, well, it looks like it's going to be negative. And sure enough it is. It'll be negative a omega squared. Here, the component of that acceleration vector is going to be in the positive x direction. And so at these 2 points we'll also get maximum and minimum acceleration. Okay. Let's fill in the following table. I'm going to fill in the first few values and let you fill in the rest of it. If theta equals 0, so that's this angle here. If it's equal to 0, then we're talking about this position here. What is x in that case? Well, we already talked about it. It's just a, the amplitude. What's vx? Here's the velocity vector. It's pointing in the y direction. So the velocity there at that point is going to be 0. What's the acceleration? Well, it's going to be pointing in the negative x direction. So it'll look like that. What about at 90 degrees? That's this point right here. Let's look at the 3 vectors. X. What is x at this point? You say, here's the x-axis, here's the y-axis. Isn't x equals 0 there? And I say, yeah, sure. Vx, here's the velocity vector. It's red. It's pointing in the negative x direction. It's going to be its minimum value, the opposite of its maximum value. And then finally, what's the acceleration? The component of the acceleration in the x direction. Here's the acceleration vector. It's green. What's its component in the x direction? And you say, well, it's 0. And I say, yeah. So I'm going to let you finish filling out this. But a couple of things. This table confirms what we talked about before, that when x is reaching its maximum or its minimum, then the acceleration is also the x component of acceleration. And when the velocity reaches its maximum or its minimum, the displacement and the acceleration are both 0. A block is hung vertically at the end of a spring. When the block is displaced and released, it moves in simple harmonic motion. Which one of the following statements is true concerning the block? The maximum acceleration of the block occurs when its velocity is 0. So here's the spring, here's the block, and let's say this is the equilibrium position. And it's oscillating back and forth from that equilibrium position. It'll get a maximum displacement. Here's x equals 0. Here's, if we measure the x direction in the direction at which the spring is being stretched, then this will be x equals a, and this will be x equals minus a. So we're measuring x down in this case. So when it's at this equilibrium position, it's moving fast. When it's at these 2 maximum and minimum positions, it's going to be stopped. Its velocity is going to be 0 up here. Here the velocity at the middle is fast. All right, so let's take a look. The maximum, and where is this going to be accelerating a lot? Well, by Newton's second law, accelerations are high when the force is high. Force is mass times acceleration. So when does this block experience the greatest forces? Is it right when it's passing through the equilibrium position, or is it when it's fully stretched down here? And you might say, well, when it's stretching that spring a lot, it's going to experience a big force, and you'd be absolutely right. That's true, that these two positions here and here, at plus A and minus A, that's where the accelerations are going to be high. All right, so the maximum acceleration of the block occurs when its velocity is 0. Well, that's true. When it comes up to the top here, reaches the top, its velocity is going to be 0, but it's going to be stretching that spring, or compressing in this case, the spring a lot, pushing down on it a lot, and the acceleration will be a maximum. So that's true. The maximum acceleration of the block occurs when its velocity is 0. The velocity of the block is never 0. Well, is that true? No. The block goes up to the top, its velocity is 0 when it reaches the top, comes down to the bottom, its velocity is 0 when it reaches the bottom, etc., etc. So that's certainly not true. If the velocity of the block is 0, its acceleration is 0. Well, also not true. Because up here, if the velocity is 0, the acceleration is a maximum. So it's kind of like the ball, the case that we talked about a lot in Chapter 3, where you throw a ball into the air, and at the peak, its velocity is 0, but its acceleration is not 0 because it has gravity pulling it down. In this case, we have the spring trying to bring it back to its equilibrium position. The maximum velocity occurs when the maximum acceleration occurs. Well, here's when the maximum velocity occurs, when it passes through the equilibrium position. It stopped up here, it stopped down here, it reaches its maximum velocity right in that center point. But in that case, the force exerted, the net force on it is going to be 0. And so the acceleration is certainly not a maximum when that maximum velocity occurs. All right, loudspeaker. Another example that I forgot to mention to you. The frequency of motion, we just ordered a couple of subwoofers for our new stereo system in our house, our home theater in our new house. So I've been thinking about this one a lot. And we'll talk a lot more about loudspeakers in Chapter 16 and 17 next semester. The frequency of motion of a loudspeaker diaphragm is 1,000 kilohertz, 1,000 cycles per second. That is about 2 octaves above middle C on a piano keyboard. The amplitude is 0.2 meters. So that means it moves 0.2 meters in this direction, comes back to the equilibrium position, and then moves 0.2 meters in the other direction for a total excursion of 0.4 meters. What's the maximum speed of the diaphragm? Well, first of all, where's that going to occur? Here and here? You say, no, the speed's 0 out there. It stops here and then turns around in both places. So it must be the maximum speed is going to occur at that center point. And the maximum speed is just what we talked about, A times omega. We have the just the regular frequency measured in hertz, but to get the maximum speed we need the angular frequency omega. It's measured in radians per second, but that's just 2 pi f. So here's my amplitude, 0.2 millimeters, so sorry. So this is actually 0.2 millimeters, and this is 0.2 millimeters, and this is 0.4 millimeters. So we've got to convert that 0.2 millimeters into meters, and to do that we just divide by 1,000. It's the same as multiplying by 10 to the minus 3 times 2 pi times the frequency. So it says that that speaker diaphragm, even though it's not moving very far, 0.2 millimeters is not very much, just moving a tiny, tiny bit. Yet because it's vibrating back and forth so quickly, the maximum speed when it reaches this point in the middle of the equilibrium position is pretty high, 1.3 meters per second.